Hello, welcome back to the class about NumPy. So now we will discuss a little bit more about metrics. So first, let's construct some metrics. So in order to build a matrix, we can do just like list in 2D. So I will say list 2D as a name of the variable, and then I say it equal to like let's say 1, 2, 3, another comma, and then I say 4, 5, 6, comma, and then I say 7, 8, 9, 8 and 9. Now what I have to do is that I will say matrix equal to np dot array, and then I put just the list in 2 dimensional in there. And now when I check the value of the matrix, it will be 2 dimensional array as we saw in the previous class. So again, we can also type this directly in the np.array. So we can say np.array, and then after we put the parentheses, then we put the bracket. That bracket is 1 dimensional. Then we put another bracket for 2 dimensional, and then we type 1, 2, 3, comma, and then we can just hit enter so that we can see it more clearly. So that we can say 4, 5, 6. We go here, put comma, hit another enter, and then we say 7, 8, 9, and then we run this cell. Oops, something wrong. Oh, a red. I typed it wrong here. Array. Now, if we check the math, then we will have the array, or we will have the same array as above. So here, the new line here is not necessary, but it is easier for us to see that it is two dimensional array. Actually, we can just type everything in one line here. Okay, like that. So we will have the same result of the matrix, something like that. Okay. So now let's do some metric calculation. So first, let's build a matrix, which is a random number between -5 and 5. So let's say matrix matrix one equal to np dot random int. Okay, and this random int I would like to be the lower bound between -5 and the upper bound of 6, which is not including 6. And then I would like the size to be, let's say 5 by 5. Now let's check the math one. Now I have the math one like that. So we have 2 dimensional array, each value between -5 and 5. Now let's build another array. Now we call this array 2, and it's also the randomly generated number between -5 and 5. Now we have the array 2. So uh, when we have when we have two matrix, so this is the matrix 1. So this is matrix 1, and we have matrix 2. So the first thing that we can do is that we can dot the matrix. We can do the inner product of the matrix. So we can say np. We can say np dot dot. So this means it will do the dot product, and then we will do the matrix 1 dot with matrix 2, and this will be the result. So if you take this matrix, and then you put this matrix up here, and then you do the simple inner product multiplication. So like this time that plus this time that plus this time that plus this time that, something like that, then we will have this kind of result. Okay, so we now have the dot product. So we also have the cross product. For example, in physics, we have the torque, like torque. Oops, we have torque. torque equal to r cross f, right? So torque is a vector. Normally we write torque with that symbol. So we have a torque equal to r cross f. So normally what we do in cross product, so we will take something like I, J, and then K. If you remember from the uh, basic metric cross product, and then you will have Rx, Ry, Rz, and then Fx, Fy, Fz, and then you will do the cross product of these metrics, right? So let's try this in our course. So let's say I would like to calculate the torque. So let's say I have R equal to the np dot array and the position vector R. So again, this is a torque. So for example, we have like a vacuum, and then we have like a particle moving like that with the force F, and we have the position vector R. So let's say R equal to 2, 3, and then minus 4, and then we have F equal to np dot array of the let's say the force is 1, 0, minus 1, something like that. So then we will have the torque. So let's see, let's say it's a big T equal to np dot cross product between R and F, and then let's print out the T. Oops, F is not defined. Oh yeah, it has to be a big F. Sorry. Now we will have the torque. So this torque will be in the it will be a vector of -3, -2, -3, something like that. Okay. So we discussed about dot product. We discussed about cross product. The next thing that I would like to talk is the common matrix in NumPy. Okay. The common matrix function in NumPy. So the first thing is that we have the identity matrix. So the identity matrix is the matrix with 1 in the diagonal direction, and everything else is 0. Everything else is 0, something like that. So we will call this the identity matrix I. And when we multiply the identity matrix to dot product with any matrix, it will return just the same matrix. So this is the identity matrix, right? So we can just do np.eye. That is very simple, and then we will just put the size, the size of the matrix. So let's say 5. Now we have the identity matrix. So let's test if it is identity matrix. So let's go up here. Let's say we have a mat1 here, like that. So I will do np dot dot. I would like to do the dot product, and then I say np dot I with the size of 5, and then I will dot this with the mat1, and the result will be exactly the same thing here, the same thing. 0, 3, 4, 0, 5, 0, 3, 4, 0, 5. Everything will be the same, but as you see, this is the floating number. So in Python, when you multiply floating number with the integer number, then it will change to float, something like that. So the next thing is the zero matrix. Zero matrix. So we have the np.0, 0 with the s here, and then we put the 5 by 5. Oops, data zeros np.0. Oh, sorry. So in order to put the size in np.0, I have to have another parenthesis there. Yeah. So now I have np.0 and it has the size of 5 by 5. So if I didn't put 5 by 5 here, for example, if I say just 5, it will be 0 array in one dimension. So if we want the array, the 0 array in 2 dimensions, we have to say, okay, 5 by 5, something like that. So again, if we do np dot dot of the np.0 of the 5 by 5, 5 by 5 size, 5 by 5 of size, and then if we multiply that metric 1, then the result will be 0 because the zeros metric multiply dot product with any metric, it will become 0. And the last thing is the 1 matrix. So np dot 1, okay, one with the s. Same thing, if we put just 5, it will be the one-dimensional array with the 5 element. So if we want 2-dimensional array, we will have to do 5 by 5, 5 by 5 like that. So so this will be the array with all the value of the element equal to 1. So if we do np dot 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 product and we say np dot ones, right? And then I want the size to be 5 by 5, and then I dot this array with the mat1, then I will have the result with something like that. So this is so we have the ones array, 0 array, and the identity matrix array. We use these array a lot when we do programming in science research. Okay, and the next thing that I would like to talk about is the reshape array. So this is quite simple. Reshape. Okay. So for example, if I have array, if I have like array in ARR equal to np.array, and then I put like a 10 number in there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. So now we will have array of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And ARR dot shape. So let's check the shape. It will be the array in one dimensional with 10 elements. So the length of the array is 10. So we can do ARR dot reshape. Then we will put the number of row and the number of columns. So if I like this to be 5 row, 2 column, I will say 5 2, 5 2. Then I will have the array in 2-dimensional with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like that. Okay, but the original array will not be changed, so it will be the same thing, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So again, so let's do like array in 2 row, 5 column. Oops, sorry. Dot reshape. I would like to reshape this into 2 row, 5 column, then it will be something like that. So how about we reshape the array to be something else? Let's say 3 and 4. So as you can see, what happened when we put 3 and 4 there, we will have the error. We will have the error notification because the program cannot put 10 elements in 3 rows and 4 columns array. So the number of the elements and the number of row and column have to be correlated to each other. So for example, next thing, if I would like to, let's say I do np.random, and I say I would like to generate the normal distribution random number, and I have 25. So I will have array in 1-dimensional. So if you see one bracket here is mean 1 dimension. Now I will just do the same thing here. Okay, let's say this is the array. Okay, array, and let's call this ARR. Okay. Now if I do ARR dot reshape, and then I say 5 by 5, as you can see, we have exactly same array, but instead of one bracket here, we have two brackets, meaning that this is one-dimensional array, and this is two-dimensional array, and we have 5 row, 5 column, something like that. And we can reshape this back. For example, we can reshape this back to the original shape uh, of the one-dimensional 25 element. It can be something like that. We can reshape back and forth, right? And or if I would like to reshape ARR uh, to be just the array of 25 row, one columns, I can do that. And then as you can see, all the value is put into dimensional, and each one will be on each row there will be only one element, and there will be 25 rows, and there will be only one column, something like that. Okay. And the last thing that I would like to talk in this class about array is the inverse matrix. This is very, very, very important. Inverse matrix. Very, very, very important. So just concentrate on this one. So in order to do matrix, first you have to import the inverse matrix uh, library. So you say import NumPy, UNPLY, NumPy dot linear algebra, LINALG, linear algebra, and then dot, and then you say no, sorry, you say from NumPy dot linear algebra, you say import inverse INV. Now this INV will be a function to invert. So let's say here INV will be the function to inverse matrix, inverse A matrix. Okay. For example, let's say above here, we have the array ARR like that. So let's change this into two-dimensional array of 5 by 5. So I will do ARR dot reshape. Let's change that to 5 by 5. Now I have two-dimensional array. And then let's put this back to matrix, right? So now we have matrix like that, two-dimensional array. So in order to do inverse matrix, it is very simple. So we can just define a new variable, say name, let's say inverse matrix equal to INV, and then we put matrix in there. Now we have the inverse matrix. So if we check the value of the inverse matrix, it will be something like that, right? How are we sure that this is the inverse matrix? So how are we sure? So for example, if we have the metric M like that, and if we have the metric inverse metric M like that, if it is the inverse matrix of M, if we do the dot product between M and inverse matrix M, it will return us the identity matrix I. So in order to do that, so let's check if we have this result. So first we will do the NP. We will do the NP dot dot. So we do the dot product between the inverse matrix, and then multiply with the matrix. Now we're gonna have something. So as you can see, we have 1, and then we have very small number in the order of 10 to minus 17. So that can be approximate as 0, something like that. So in order to see this more clearly, right? So let's say I will do the dot product and then I will do dot round. So I would like to round this number to the nearest integer number. So when I did that, then I will see the results of identity matrix. So this is one. There is one in the diagonal direction, and all the rest of the elements of the array will be zero. So this is the identity matrix. So the minus zero here is mean is this the value of zero, but is this approaching from the negative direction? So you don't have to worry about that. It is a zero, like very small number, but is this a negative number close to zero, something like that? Okay. So I think, let me see if I have anything else. Nope. So I think that is everything I would like uh, to talk about. Let's see one example of how to do the application of the inverse matrix. Okay. Okay. For example, we have this set of equation. So we have the equation of 2x here, 2x plus 3y plus 4z equal to 9. We have like minus x minus y plus 2z equal to minus 7 and x minus y plus z equal to minus 2. And this is the answer. This is the answer of x, y, and z. But for example, but suppose that we don't know these. We don't know the answer of x, y, and z. So if we only have the equation, the set of equation like that, how do we calculate x, y, and z? We can simply do that by uh, by setting. So we can write it as a matrix. So we can write a matrix of x, y, and z. Now we will put the constant here as another matrix: 2, 3, 4, minus 1, minus 1, 2, and then 1, minus 1, 1, something like that. And then the result will be another vector of 9, minus 7, and minus 2, and minus 2. So if you do the dot product between this matrix and this vector, it will just give you back this equation, right? So now let's say we have let's say I will call this I will call the matrix M. It multiply to the vector xyz, let's say the vector v, and it will be equal to the result. Here is the result. Let's say VR as the result. So in order to find the value of xyz here, we want the v, which is the vector of the xyz. What we did, or what we will do, is that we will multiply everything with the inverse matrix of M. So let's say oops, sorry, I accidentally deleted. So again, let's write it again. We have the vector, we have the matrix M multiplied by the vector of xyz, which I wrote as v in the previous one, and then I have the result. And I have the result of I can't remember. Is okay. Now I can bring this back. Okay, now we have the metric. Now we have the metric M times the vector v. The vector v here is the xyz. Okay, let's change the color a little bit. And now the result here is here, the vector result. So in order to calculate the vector v here, we will just multiply everything multiply everything by the inverse metric of m. So we will multiply this as well. So let's change this color. So let's delete this one in case, like, suppose that we don't know the result. We don't know the result. So we will multiply the inverse metric to everything, right? So this inverse metric will become identity matrix. So we'll have just only V here, and then we will have the inverse metric times the result. And this is the way we calculate X, Y, and Z value. So let's do this example. So in order not to delete everything again, so I will write 2, 3, 4, -1, -1, 2, 1, -1, 1 here as the m, and then I will have the 9, -7, -2 there as the result, and then I will delete everything. I will delete everything. Okay. Okay, now, so what I'm gonna do here, I'm gonna say, okay, matrix, my matrix is the two-dimensional matrix. I will say np.array, np.array, and then it will have the first element of 2, 3, 4, right? The second row of the element will be -1, -1, and then 2, and then the third row of the element will be 1, -1, 1, 1, -1, and then 1, right? Oops, something wrong. Oh, I forgot to put another bracket there and there. Oops, oops, bracket, not the curly bracket. Okay, now I have the metric like that. So I will have the inverse metric inv of the metric equal to inv of the metric, right? So let's check the value of the inverse metric. Now I have this is as the inverse metric. Now I have another, let's say, result. Let's say result equal to the np.array. Now this is array of the 9, -7, -2, right? So let's show the result. Okay, now I have the inverse metric already. So I have, so this is the m. So this is the metric m. And now I have the inverse metric already like that. And this is the metric result. And I have put it here result. So what I need to do here is that I will just do np dot of the inverse metric, like, and I will multiply with the result, right? And then I will have 2, 3, and -1 as we expected for the value of x, y, and z in the beginning of the example, right? So as you can see, we can use metric to solve math problem. And in the next class, where we will start doing some finite different method, the metric multiplication with the inverse matrix will be used a lot, and it will be very, very useful to do that kind of application in science research. Okay, so I think this is everything I want to discuss today, and thank you so much for your time, and see you in the next class, and happy coding. Bye bye.